We just reviewed what a relation is, and now I want to explore the properties of relations.
The first property is the reflexive property, and a reflexive relation is a relation where A comma A is in the relation. So essentially the x and y values will equal one another for all of the A's. So the question is, which one of these four relations are reflexive? And these should look familiar to you because we just talked about them. So which ones are reflexive? The question is, could I, if I'm entering values into R1, is it true that all A comma A's would be in this relation? And of course the answer is yes, because A does equal A. The other relation that would work for reflexive is R2. So R1 we said was yes. R2, remember, as long as A is less than or equal to B, that means the two values A, we're saying A is less than or equal to A, and that of course is absolutely true. So AA would be a set, or excuse me, an element in that set. The others would not work because A cannot be greater than itself, and so obviously AA is not an element of that set. And A plus A is not always less than or equal to 3, so it would work for 0, 0 or for 1, 1, but not for any other points. And so remember, in order for it to work, it has to work for every A that belongs to that set. So our answer here is only R1 and R2. The next property is the symmetric property. So a relation is symmetric if and only if BA belongs to R whenever AB belongs to R. So essentially we're saying if AB belongs to R, then BA must belong to R. So which of these relations would be symmetric? Again, let's take a look. If I have a value, say 2, 2, that belongs to R1, because obviously 2, 2 would belong to R1, then the question says if it's symmetric, then if I switch the order, it would also belong to R1, and of course that's kind of a give me. Yes, this is going to be symmetric. For R2, we're saying A is less than or equal to B, and so let's say I had 3, 4. 3 is less than or equal to 4. If I switched these, 4, 3, that's the question, is that also in R2? And of course the answer is no, because 4 is not less than or equal to 3. So even though it would work for some, like 3, 3, it doesn't work for all. R3, remember this is that A is greater than B, and again this is going to be similar to R2, where if I said 4, 3, and then I switch them to 3, 4, 3, 4 is not in the set, so R3 is not symmetric. And last one, if A plus B is less than or equal to 3. So again, we're not saying does it work for all values in the set, we're saying if A comma B is a value in the set, like say 0, 0, or 0, 1, or 3, 0, you get the idea. The question is, if all of these values are in there, is it also true that if I switch the order, they're in there? So is 0, 0 in there? Yep, that's less than or equal to 3. Is 1, 0 in there? Yes, that's less than or equal to 3. Is 0, 3 in there? Yes, that's less than or equal to 3. So this one is true because it specifies that if this is in there, then BA is in there as well.
Anti-symmetric is not the same as saying something is not symmetric, which seems a little silly, but anti-symmetric essentially says this. It says if A and B are both elements of A, and A comma B and B comma A are elements in the relation, that implies that A is equal to B. So if we were thinking about this in terms of our logic, we would be saying if for all A and for all B, A comma B belongs to R, and B comma A belongs to R implies, I think I need an extra parenthesis, implies A equals B. So that's what we're talking about. So this is an implication. So we are going to look at these relations and say whether or not they are anti-symmetric. Looking at the first one, we have R1 is all of the elements A, B such that A is equal to B. So this one seems kind of silly because we're saying if A, B is in R and B, A is in R, well, we know that for every A, B that's in R, B, A is going to be in R because they're always the same. So 5, 5 is in R, and then switching the order, 5, 5 also is in R. So yes, of course, this is true. For all of those elements, A, B, and BA that are in R, that implies A is equal to B. And we can continue to make a listing of them, but it's not necessary. We know that this one is true. For R2, again, this part's really important. This part has to be true. So we're saying for all of the elements A, B, and BA that are in R, then it's true that A is equal to B. So you might have an argument that says, okay, well, 3 is less than or equal to 4, but 4 is not less than or equal to 3, and therefore it's not antisymmetric. But remember, this whole part needs to be true in order for us to look at the implication. So I don't even have to look at ones that are not in where both A, B, and BA are not in the relation. So let's take a look at something like 2, 2. 2, 2 is in the relation because 2 is less than or equal to 2. And if I switch the order, 2 is less than or equal to 2 is in the relation as well. And does that imply that A is equal to B? Yes. So are there any counterexamples that I can find? So again, 3, 5 is in the relation, but when I switch it, 5, 3 is not in the relation, and so therefore it doesn't even pertain to the question I'm asking. So I'm only asking for if it's true that both of these are in the relation, then A must be equal to B. So this one's actually true, and it's true because of this or equal to situation here. Let's take a look at 3. A is greater than B. So if A is greater than B, let's say I have 4, 2. So 4 is greater than 2. I wrote it as obviously as an inequality, but let's just write it 4, 2. 4, 2 is in fact in R3 because 4 is greater than 2. 2, 4 is not in R3 because 2 is not greater than 4. So again, just like we talked about here, we're only concerned about items that are where both A, B, and BA are in the relation. And it's never going to be true that A is less than B, that A is greater than B, and that B is greater than A. So you might be saying, well, therefore R3 must not be antisymmetric. But again, remember when we had an implication, and I'll just make it a little easier. If we have if P then Q, and P was false, remember what happened to Q? Q was true. It was vacuously true, we called it. And so that's exactly what's going to happen here. And then for R4, again, we're saying AB, A plus B is less than or equal to 3. So can I find a counterexample? 2, 1, is that in R4? Yes, 2 plus 1 is less than or equal to 3 because 2 plus 1 is 3. And is 1, 2 also in R4? Yes, 1 plus 2 is less than or equal to 3 because 1 plus 2 is 3. Does that imply that these two are equal, that 2 is equal to 1? No, it does not. So, therefore, R4 is not antisymmetric. Now let's take a look at the transitive property. This is our last property. And we're not going to do a proof for any of these, so just I haven't stressed that as I've gone through the other examples. Remember that we would actually have to do a mathematical proof to say definitively that this is true for all values, and that's the key point here, is that we're looking at all values. In order to say yes definitively, we would have to do a proof. You and I are just going to reason through this together. In order to say no, all we have to do is find a counterexample. So in this case, when we're looking at transitive, we're saying whenever A comma B is an ordered pair in the relation and B comma C is an ordered pair in the relation, that implies that A comma C must also be an ordered pair in the relation. So if I can show that that's not true by some counterexample, then it's not true, even if there are elements that actually work. But if I can reason through it and say it's always going to be true, then we're just going to go with it even though it's not a formal proof. So let's look at R1. A comma B, where A is equal to B. So 2 comma 2 is the sample type of ordered pair in that relation. Now what we're saying is this second element of the ordered pair is going to match the first element of the next ordered pair. Now if my next ordered pair starts with a 2, then according to my relation, then the second part of my ordered pair must also be a 2 in order for it to be in the relation. So this is saying whenever 2, 2 is in the relation and 2, 2 is in the relation, then that implies that what is in the relation? Well, now we're looking at the first part and the last part. So does that imply that 2, 2 is also in the relation? Yes, it does. And it works for every ordered pair that we can come up with, because all ordered pairs in R1 have A equal to B, and so it's always going to be true. Say that if 7, 7 is in the relation and 7, 7 is in the relation, then 7, 7 is in the relation. So that one's, again, kind of a silly one, but R1 is in fact transitive. Let's look at R2. Let's come up with an ordered pair, say 2 comma 5. 2 comma 5 is in the relation because 2, which is A, is less than or equal to 5. And then again, my next one has to be 5 comma something. And again, I'm just making up an example so that we can reason through it. We know that in order for 5 comma something to be in the relation, that B has to be obviously greater than or equal to 5. So let's just think of a number like 8. Now, knowing that this guy always has to be less than this guy, and this guy always has to be greater than or equal to this guy, can we say that it's always true every single time that that value will be in the relation? I should have stuck with my same color scheme here. And in fact, we can. It's always going to be true. So even if I used a 2 here because of this or equal to, so even if I used a 2 here, obviously that goes back to this example here, where that's always going to be true. And we can see, using that same reasoning, that R3 is going to be true. If I've got some number A that's greater than B, so let's say this guy is 4, and of course there's no or equal to in this case, so this one's say 4, 3, and this one's 3, 0. Is it always going to be true then that 4 is greater than 0? It is always going to be true every single time, because we know that these values must keep decreasing, not by 1 or by 2, but just has to be less than the value before it. And let's look at the last one. We have A plus B is less than or equal to 3. So if AB, let's say 3 comma 0, is 3 comma 0 in R4? Well, 3 plus 0 is 3, which is less than or equal to 3, so this guy is in R4. Now, is 0 comma 2 in R4? Well, 0 plus 2 is less than or equal to 3 because 0 plus 2 is 2, so yes. Does that imply then that 3, 2 is in R4? Well, 3 plus 2 is 5, and 5 is not less than or equal to 3. So again, this isn't a proof, but this is a counterexample. And as long as I have one counterexample, I can say that it's not true for all of R4. So even though I could come up with one example or two examples where it is true, if I can find one counterexample where it's not true, then I can say that the entire relation is not transitive.
We're going to take a look at just one more example, and in this case, as you can see, we're dealing with a relation that is simply a list of ordered pairs. So in all of the other questions, I didn't actually list the ordered pairs. I gave you some sort of property that related A and B to one another. Quite often you'll just get a question like this where they are giving you the list of ordered pairs, and of course, importantly, they are giving you the set at which the relation is on. So let's just get started doing the exact same thing. If you feel comfortable, I would like you to press pause and try this question on your own. If you don't, that's okay. We'll go through it together. So we'll start with reflexive. And remember, the reflexive property says A comma A, that was the wrong set bracket. I just need A comma A is in R, essentially for all A's that are in the set. And so that makes it pretty easy to check. My set contains 1, 2, and 3. This is my set. And so all I have to do is check, does it contain 1, 1, 2, 2, and 3, 3? So if I take a look at my relation 1, 1, 2, 2, and 3, 3 are in fact in the set. So I can either say yes, R, 1, 1, 2, 2, 3, 3 are in the relation, or I can say this. For all A's in the set, A comma A is in the relation. Either way. All right, let's take a look at another property, the symmetric property. The symmetric property says that if A and B is in the relation, that implies that B comma A is in the relation. So let's check. We have 1, 1, and if I switch the order, that's 1, 1, and that's in the relation. I have 1, 2, and if I switch the order, that's 2, 1, and we can see that's in the relation. I've got 2, 1, which I already know the symmetric ordered pair is also in the relation, 1, 2. I've got 2, 2, and if I reverse the order, that's 2, 2, that's in the relation. And then of course I've got 3, 3, and that's the same thing. So again, this is a yes, and I'm going to say for all A comma B's that are in the relation, B comma A is in the relation, which is essentially the symmetric property. So really, if I'm saying yes, I'm just saying yes, that property is met. All right, let's try anti-symmetric. Anti-symmetric says that if both A comma B and B comma A are in the relation, that implies that A is equal to B. So 1, 1 and 1, 1, yes, that works. That's A comma B, B comma A, and A is equal to B. What about 1, 2? 1, 2 is in the relation, and if I reverse the order, 2, 1 is in the relation, but 1 is not equal to 2. So this is a no. And then instead of listing or writing out what the anti-symmetric property says, I'm going to give the counterexample. That 1, 2 and 2, 1 are both contained in the relation, but 1 is not equal to 2. And then for the last one, the transitive property, this is the least fun to check. The transitive property says if A comma B and B comma C are in the relation, then A comma C is also in the relation. And so really I've got to check this one just the long way. So let's give it a try. If I have 1, 1, and say 1, 2. So really when I'm doing this, I'm looking at the last or the second part of the ordered pair and the first part of the next ordered pair need to match up. And does that imply that 1, 2 is in the relation? And yes, 1, 2 is in the relation. All right, so let's check it with 1, 1. And anything else? Nope, nothing else, because nothing else starts with 1. Okay, so let's try with 1, 2. 1, 2 and 2, 1. Does that imply 1, 1 is in the relation? Yep, that's there. All right, let's try 1, 2 and 2, 2. Does that imply 1, 2 is in the relation? Yes, that's there. Let's move on to the next ordered pair. 2, 1 and, whoops, wrong one. 2, 1 and 1, 1. Does that imply 2, 1 is in the relation? Yes, it's there. All right. Anything else for 2, 2? 2, 2, 2, 1. Does that imply 2, 1 is in the relation? Yes. And then of course 3, 3, 3, 3, that implies 3, 3 is in the relation. So while it's a real pain in the butt to check them all, that's what you have to do. So we can say yes for all A, B, B, C that are in the relation. That implies that A, C is in the relation. So hopefully that gives you a better idea of dealing with these properties when the relation is actually a set of ordered pairs.
Up next, we're going to take a look at combining relations.